functionalities of data link layer. So we already know what are the functionalities. Functionalities are error control, flow control, framing, etc. Actually, data link control layer has a sub layer that is called MAC sub layer or median access control layer. So all those things will be discussed in due course. So as a first topic of data link layer, we will start from error control mechanism. Okay.
আগের দিন ওটা কি লাস্টে বলবেন?
হ্যাঁ,
আগের দিন যে প্রবলেমটা বলেছিলাম আপনাকে পরে এও করেছিলাম, মেসেজও করেছিলাম।
পরে মেসেজ করেছি কি বলো তো একটু কোন ব্যাপারটা একটু বলো।
হ্যালো
হ্যাঁ বলো। কোন ব্যাপারটা?
হ্যালো
কোন
হ্যালো শোনা
ব্যাপারটা?
যাচ্ছে?
হ্যাঁ, কোন
হ্যালো শোনা
ব্যাপারটা বলো।
যাচ্ছে?
হ্যাঁ,
বলছি এফডিএম সলিউশনে যেটা বলেছিলাম আপনাকে, এফডিএমটা একটু বুঝিয়ে দিলে।
এফডিএম টা। একটা মিনিট। আচ্ছা ঠিক আছে, এটা আমি স্টার্ট করি। এফডিএম টা আমি বলে দিচ্ছি। ঠিক আছে, তুমি একটুখানি শিখে যাও দরকার হলে, বা তুমি বা তোমরা যাদের যাদের দরকার ক্লাসের পর। So our first topic of data link layer is error detection and correction. So these are the two important parts in error control mechanism. There is a tiny difference between error detection and correction. In error detection, we will detect whether any error occurs in the bit stream or not. But in error correction, first we need to detect whether any error occurs or not. Then we have to find out at the exact location where the error occurs. If we can find out the exact location, then definitely um, error can be definitely error can be removed. How? Because we are sending only binary data. Data contains only value zeros and ones. Suppose we have found out that fifth bit is erroneous. So there is an error in fifth bit in a bit stream. So we have located the location, we have located the position where the error occurs, and we have found that at, at fifth bit value 1 is there, and if it is error, then obviously the corrected value should be 0. Okay, if we find out value 0 in the erroneous position, obviously we will complement it. We will complement that particular bit value. So if 0 is erroneous, so obviously value 1 will be the corrected value. Okay, and this facility is achieved only for binary number system. This method or this procedure cannot are not suitable for any other number system, as there are more than two digits are presented, more than two digits are present in other number systems. In octal there are 8 digits, in decimal there are 10 digits, in hexadecimal there are 16 digits. Okay, so it is very difficult to find out the error in other number systems. That's why always we prefer, not prefer actually, always we send data in a binary format. So while we transmitting data, the data value can be corrupted during the transmission, and it can happen for various purposes, for various factors. Okay, maybe some extra noise is incorporated within the signal. Especially, it is very obvious while we transmitting the data in an unreliable medium, through an unreliable medium. Unreliable medium means suppose twisted pair. Okay, so twisted pair, if we use especially unshielded twisted pair, there is a possibility to there is a possibility that the original signal can be affected with by external signal. But that can be minimized if we transmit the data value through fiber optic or maybe through coaxial cable. Okay, the signals passing through coaxial cable or fiber optic are um, uh, those are comparatively secure because the external interference will be minimum at that point. But it is not possible for us to use a coaxial cable or fiber optic for every connection because these are very costly. Fiber optic communication, coaxial cable communication are very costly. So that's why we have to use twisted pairs, especially unshielded twisted pairs, to minimize the setup cost. That's why we have to focus on error control. So if our main goal is to first detect an error, whether any error occurs during the transmission or not. If error occurs, then we will try to solve that error. We will try to correct that error. Okay. So for correcting the error, we need to identify the exact location where the error occurs. Okay. So this is the basic error detection model. Sender will send a message and something is generated with the help of generator. Now this generator actually generates the different error correction technique. Okay, so we will see some error correction technique later. Then message is generated, a new message is generated. Normally some redundant bits are added or sometimes one redundant bit is added along with the original message to detect error. And then that message is transmitted in the receiving side. And here it is written that unreliable transmission. Why it is unreliable? Because there is no reliability with respect to error. Okay. So in we studied that reliability factor was there in TCP and UDP also, but that reliability was in some other context. In those cases, the reliability means the exact data, the data has been reached to the correct recipient or not. But in this case, in data link layer, every transmission is unreliable because we do not know when the data value is affected by the external sources. So some noise can be attached, can be associated with the original signal. Hence, it error occurs. So what is happening in the receiving side? Receiver first receives the information, then it checks. While it checks, it if the data value is correct, then it will accept that message. Otherwise, it will discard that message. Okay. Or it will try to find out the error. So error can be divided into two different types. One is called single bit error, where only one bit value has been changed in entire bit stream. The example is given. Sender sends data value 00000010, but ultimately receiver receives the data value 00001010. So this zero, the marked one, this zero has been changed to 1. So how many bit has been changed? Only one bit has been changed. That's why it is called single bit error. On the other hand, there are multi-bit errors, that is also called burst error. In burst error, two or more bits can be changed in the data unit. Suppose sender sends this data value, but during the transmission, some of the bits are corrupted. So ultimately, receiver receives these bits. So here we can see 4 zeros are converted to 1. 4 zero values are converted or changed to 1. So whatever data value received by receiver is wrong basically. Okay. So hence this situation leads to error. Different techniques to detect error. So those different techniques are redundancy method, modular arithmetic method, forward error correction method, and retransmission method. In case of redundancy method, we add or append some extra bit or bits. Sometimes only one extra bit is added or appended, or sometimes more number of bits, more than one bits are appended along with the original message, and then the message is transmitted. Okay. So this extra redundant bit is used to detect it. Okay. So many examples are there that uses those redundant bits, like parity method.
স্যার
Parity,
আরেকটা কোশ্চেন
huh?
স্যার, আমার একটা জিজ্ঞেস করার ছিল স্যার।
হ্যাঁ বলো।
স্যার বলছি, ধরুন আমরা একটা ডেটা সেন্ড করছি, তো রিসিভার ওটা বুঝছে কি করে যে ওটার মধ্যে এরর আছে?
হ্যাঁ, তোমার তো এরার কন্ট্রোল মেকানিজম তো তোমাকে দিতে হবে। এরার কন্ট্রোল মেকানিজমটাই তো আজকে পড়বো।
মানে ওটা রিসিভারের কাছে অলরেডি তাহলে একটা টাইপ অফ কিছু আছে যেটার জন্য রিসিভার বুঝতে পারছে যে
মেথডটা বলা আছে প্রোটোকলে। যখন তুমি কমিউনিকেশন করবে তখন আগে তো তোমাকে প্রোটোকলটাকে এস্টাবলিশ করতে হবে। তো প্রোটোকল এস্টাবলিশ করা মানে হচ্ছে একটা মিউচুয়াল একটা এগ্রিমেন্টে আসা, যে আমরা এতটা ডেটা পাঠাবো, এই ডেটা পাঠাবো, হ্যাঁ, এই এরার কারেকশন মেথড ফলো করবো। তো যেমন ধরো তোমরা অলরেডি ছোটবেলায় পড়ে এসছো প্যারিটি বিট। প্যারিটি বিট দিয়ে ডেফিনেটলি তুমি তো এরা ডিটেক্ট করতে পারো।
হ্যাঁ স্যার।
তো সেরকম একটা মেথড
কিন্তু স্যার
সেইরকম। হ্যাঁ,
কিন্তু স্যার রিসিভার কি করে বুঝছে যে সেন্ডার কি পাঠিয়েছে অ্যাকচুয়ালি ডেটাটা? তাকে তো রিসিভারকে তো জানতে
না
হবে তাহলে যে ডেটাটা কি পাঠিয়েছে অ্যাকচুয়ালি, তারপর তো আমি খুঁজে বের করবো যে ডেটাটা চেঞ্জ হয়েছে কি হয়নি,
না,
মডিফাই হয়েছে কি হয়নি।
ওই যে বললাম এখানে দুটো পার্ট আছে, একটা হচ্ছে এরার ডিটেকশন, একটা হচ্ছে এরার কারেকশন। ঠিক আছে, কি ডেটা পাঠিয়েছিল আর কি আমি রিসিভ করেছি সেইটা কিন্তু কম্পেয়ার করবে না, শুধু কম্পেয়ার করবো যে এরার আছে কিনা সেটা দেখবো। ঠিক আছে, একটু ওয়েট করো, মেথড গুলো একটুখানি আলোচনা করতে দাও, আমার মনে হয় তোমরা বুঝতে পারবে যে কিভাবে কাজটা হচ্ছে। ঠিক আছে, স্পেসিফিক্যালি যখন আমরা সিআরসিটা আলোচনা করবো, সিআরসি চেকসাম এইগুলো আলোচনা করবো। ঠিক আছে, ইনিশিয়ালি আমরা স্টার্ট করবো প্যারিটি বিট দিয়ে, কিন্তু দেখো প্যারিটি বা 2D প্যারিটি, 2 ডাইমেনশনাল প্যারিটি, এগুলো এরার কারেকশন এরার ডিটেকশনের জন্য ইউজ হয় না। ঠিক আছে, অনেক বছর আগে হয়তো ইউজ হতো ইনিশিয়ালি, কিন্তু এখন ওগুলোর কোনো মানেই নেই, অপশনই। কিন্তু সিআরসি কিন্তু ইউজ হয়। তোমরা অনেক সময় দেখবে যখন কোনো ফাইল কম্প্রেস করো, ওই সময় অনেক সময় রিমার্কস বা স্ট্যাটাসে লেখা দেখায় সিআরসি ওকে বলে। দেখেছো তোমরা বিশাল?
স্যার মনে পড়ছে না।
যাই হোক, এরপরে তাহলে খেয়াল করো, অনেক সময়, সব সময় হয় না, কিভাবে কম্প্রেস করছে না করছে, এবং কম্প্রেস যখন আমরা আনকম্প্রেস করছি তখন কি আমার এটা অ্যাপিয়ারেন্সটা কি শো করছে তার উপর ডিপেন্ড করে। তো অনেক সময় এটা খেয়াল করলে দেখা যায়। ঠিক আছে, সেই সিআরসি টেকনিকটাই আমরা করবো, তখনই আমরা দেখবো। হ্যাঁ,
সিআরটি বললেন?
সিআরসি, সাইক্লিক রিডান্ডেন্সি চেক। ওখানেই আমরা দেখবো যে কিভাবে রিসিভার বুঝতে পারছে যে এখানে এরর আছে। ঠিক আছে, জাস্ট ফর সামথিং। The next error detecting technique is modular arithmetic. So different types of arithmetic operation is performed to detect error. Okay, so checksum is one of the example of this modular arithmetic. Uh, uh, the name is given modular arithmetic, but actually not only arithmetic. Sometimes we use JOR operation also. So in those JOR operations are incorporated in those techniques. Okay. Next, in forward error correction, it is the process where receiver tries to gauge the message by using redundant bits, but This method is suitable for small error or for small message. It is not useful for detect error for bigger message or larger message. The most easy one is the retransmission, a technique where receiver detects error, the occurrence of an error, and asks resend the message. So receiver will not spend any time to rectify that error. So if our protocol adopt retransmission, in that case, error correction mechanism will not be implemented. Only error detection mechanism is implemented. The receiver will detect whether any error occurs or not. If error occurs, receiver simply discard the message and will send a message to the sender that your previous message was corrupted, so please resend it again. Okay, that is retransmission. Next, we start our. Okay, there are some characteristics, more characteristics for error detection. In case of error detection mechanism, the receiver knows an error occurs, but doesn't know where the error occurs, exactly which bit value has been changed. So the location of the error is not detected. As a whole, the error will be detected. An error detecting code can detect only the types of error for which it is designed, but other types of error cannot be detected. Suppose if we adopt parity method to detect error, parity method is useful to detect single bit error, especially. So if two data values has been changed, we cannot detect these things with the help of parity, because parity is designed only to detect single bit error or specifically odd number of error. Odd number of error means odd number of bit value has been changed in the entire bit stream. So we will describe these four methods, error detection method: simple parity check, two-dimensional parity check, cyclic redundancy check, and checksum. Out of them, CRC and checksum is widely used. So all of you know the basic principle behind the parity method. You have already studied this in uh, second semester, as far as I remember. So two different types of parity is there: even parity and odd parity. Even parity tells us that including parity bit, the total message in the total message, the total number of one should be even. Okay. Here we are using a term that is code word. You can see code word. That term is used. Code word means, suppose I want to send a message, and some redundant bits are added with the message, are appended with the message to detect error. So while I am trying to retransmit the data value to the other side, that redundant, the original data value along with the redundant bit or bits are sent to the other end. That is called code word. Okay. So while we transmitting the code word, if we follow even parity, then in the code word total number of one should be even. But if we follow odd parity, it ensures that there are odd number of ones in the bit stream, in the transmitted bit stream. Okay. So here you can see this is even parity. This is the example of even parity. Here we want to send data value 0000, but in code word you can see an extra 0 has been appended. 1, 2, 3, 4, 5. Instead of 4, in the code word 5 zeros are there. So this is the extra or redundant bit that is appended along with the original data value. This is called for parity bit. Now we have to find out what will be the value of the parity bit. In the first case, actual data word or actual original message, all 4 zeros are there. There is no 1. And we are following the even parity strategy. So, what should be the parity method? What should be the value of the parity bit? Parity bit cannot be 1. Because if the parity bit is 1, then in the code word there will be odd number of 1. And that cannot be happen because we have adopted even parity strategy. So, the parity value should be 0. But what will happen in the other case? Suppose I am taking a separate example. Suppose 0010. In the actual information, 0010 is there. So how many ones are there in the actual bit stream? Single one is there. That is the odd number of 1 is there. So we have to select the parity bit value according to that, so that including the parity bit, there should be even number of 1. That's why here you can see in the third row, as the LSB, another 1 is added. This is actually parity. Okay, LSB তে আমরা parity টাকে দিয়েছি। তাহলে actual data value was 0010. Here it is 0010, and parity bit value 1 is chosen to make it even. Okay. Okay. We can see another example. Suppose data value is the 5th row, right hand side column. Actual data word is 1100. So how many ones are there? Already even number of 1 is there. So as a parity bit, we will select the value 0, not 1. Because if we choose value 1, then including the parity bit, there will be 3 number of 1s. There will be an odd number of 1s. So that cannot be happen as we have chosen even parity. So for this case, the parity bit value should be 0. Clear? এটা আমরা অলরেডি পড়ে এসেছো, জাস্ট রিক্যাপ হলো। ক্লিয়ার তো? হ্যালো হ্যালো হ্যালো, শোনা যাচ্ছে আমার কথা?
Yes, sir. শোনা যাচ্ছে।
তাহলে রেসপন্সটা দাও। আমি যখন জিজ্ঞেস করছি চুপ করে থাকলে হবে? আমি বুঝতে পারবো তাহলে? ওকে, okay, this is the encoder or decoder part of simple parity check code, or we can say generator and checker part. Okay, here it is the actual data word A3, A2, A1, A0. Okay, the 4-bit data word is chosen here. So from these 4-bit data word, we are selecting a parity bit. Parity bit is chosen. So for that, parity generator can be used. Now this total code word. So along with that original data value A3, A2, A1, A0, the parity bit value R0 is appended, and the total code word is transmitted to the other end. So other end checks that parity bit value, and if there is no error, it will accept this one. Otherwise, the design logic or the parity checker will discard the message. But if there is no error, then it will accept the message. Next, two-dimensional parity check. So here the principle of parity bit is same, but instead of using the parity bit for only 1 byte, we can use it we can use the method, we can use the principle in a modified way. So what is the modification? The modification is the total bit stream is divided into different groups. Suppose here the total bit stream is divided into 4 groups, and in each group actually 7 bits are there. So you can see, and all those groups are placed row wise. Okay. Just a minute. So that means basically all the bit values are arranged in a tabular form. All bit values are arranged in a tabular form. Now we have to find out the parity for all the rows, all the row values, and then we will find out the parity for columns also. Okay. So in this case, we can take the row values for the first one. In the first row, 1, 1, 0, 0, 1, 1, 1. So these are the actual 7 bits in the original message. So we will count how many number of ones are there. 1, 2, 3, 4, 5. 5 ones are there. So if we follow the even parity method, then the parity bit for the first row should be 1. Okay. The same thing happens for the second row also. But for the third row, the bit value is 0, 1, 1, 1, 0, 0, 1. So first checks how many number of ones are there in the original method. 1, 2, 3, 4. 4 ones are there. 4 ones are there. That means already even number of ones are there. So the parity bit value should be 0. So in this way, row-wise parity is generated, and in the same way, column-wise parity is also generated. Okay, so column-wise parity is also generated. So by using row parity and by using column parity, we will be able to detect if there are more number of errors in the parity. So here you can see one error is affected. There is only one error, but it affects 2 parities. Okay, that are shown with the arrow mark. So if the original value was 0 and it is converted to 1, that is marked in the second row, you can see. If this is an error, that means this error actually affects the row parity as well as the column parity. Okay. Now here you can see the 2 different errors can affect 2 different persons, two different parities. Okay. Here the values are changed in same row, so that cannot be. That may be not detected by row parity, but that should be detected by column parity. Here is some more example of 2-dimensional parity. Next, we will shift to cyclic redundancy check method. Here also in the same way this happens, but the method is something different. Now we will discuss the method here. This is the example, okay, of CRC. Suppose we want to send data value 11001. This is the data value we want to send. Okay, so this is the dividend. Now we have to find out, we have to agree upon a divisor value. So what should be the divisor value? So according to the protocol, divisor value is chosen. Suppose for this example, divisor value is 1011. Now we will append some data along with the original data word. So how many data has been appended? N minus 1 bit value should be appended, where n is the number of bits present in the device. So here we can see in divisor 4 bits are there. 1011. This is the value of the divisor. So the length of the divisor is 4 bits. So n is equal to 4. So n minus 1. So 4 minus 1. 3 bit values should be appended along with the original data word. And those bit value was initialized with 0. That's why you can see 3 zeros are appended along with the data value. Okay. Now we will perform the operation. What will be the operation? This is not exactly the division method. Okay. This is not exact division method, but we follow division like method. Let's see how this method works. One condition is there. The MSB value of the divisor should be 1 always. It should not be 0. Okay. This is only one condition. So we have to select the divisor value according to that. So first we will see the MSB of the divisor should be 1. So, and the divisor length is 4 bits. So we will first take first 4 bits from the dividend, and we will check whether the first bit value of this partial dividend is 0 or 1. If it is 0, then obviously it goes 1 time, and we will write here 1011 and we'll subtract this one. So this is the first point where it differs from the original division method. Original division method আমাদের কি করতে হয়? We have to check whether the dividend value is greater than the divisor value or not. If the dividend value or the partial dividend value is greater than the divisor value, then it is okay. But if not, then we have to take an extra bit or extra digit for the division. But here the things are little bit different. Here we will concentrate on the length of the message only. So length of divisor bit is 4. So we will take first 4 bit from the dividend and check what is the first bit value of the dividend. That is the MSB bit value of the dividend. If it is 1, then it goes 1 times. So we will write the divisor here, actually 1011, and we will subtract. Okay, but again, it is not the normal subtraction. Basically, we will do bitwise subtraction here, and bitwise subtraction is nothing but a XOR operation. You will see here. This one, that one represented with magenta color, this one should be subtracted from 1, so bit value, so result is 0. Then in the next higher order bit there is 1, that should be subtracted from 0. So difference should be 1, and there should be a borrow. But where is the borrow? The borrow is this one. So we will subtract bitwise. Okay, the borrow will not affect. The borrow occurred, the borrow generated in one location is not affected for any higher order bit. That borrow will be discarded. Then again it is 0, subtracted from 0, it should be 0. So what will happen? If we subtract 1 from 1, our result will be 0. If we subtract 0 from 0, our result will be 0. If we subtract 0 from 1, normally our result is 1. If we subtract 1 from 0, actually our result should have been 1, 1. One should be the difference and one should be the borrow. But here that borrow is discarded. So we can assume that if we subtract 1 from 0, our result is 1. So if you like this in a tabular form, you will see the things are very much similar to the XOR gate footprint. So basically, we are performing bitwise XOR operation. So after subtracting this, after subtracting the divisor from the partial dividend, we will get 0, 1, 0. So 3 bit values are there. So we have to pull down the next bit, that is 0 here for this example. Now the partial dividend becomes 0, 1, 0, 0. And the MSB value is 0 for this partial dividend. So it goes 0 times. So if it goes 0 times, then it is all 0. So we subtract this from the partial dividend. We will get the new partial remainder, that is 1, 0, 0. 0 minus 0, 0, 0 minus 0, 0. 1 minus 0, that is 1. Next, we will pull down the next 0. It becomes 1, 0, 0, 0. That is the partial dividend. So MSB of the partial dividend is 1. So it goes 1 times. And we will subtract it again. So 1 minus 0, 1. 0 minus 1, 1. 0 minus 1, 1. 0 minus 0, 0. Then we will pull down the last bit. Last 0 is pulled down. Again, the leftmost bit is 0. So it goes 0 times. So the divisor used here, that is 0, 0, 0, 0. Then we subtract. We not subtract, bitwise subtraction is performed. So ultimately the remainder is 1, 1, 0. So that is actually the CRC. Now what we will do? We will redefine our code word. Okay? Whatever the remainder is, that remainder is appended along with the original data word. Our original data word was 1001. So here it is 1001. Then this remainder 110 is appended, not added. Okay, addition hocche na kintu append hocche, just like string concatenation. So it is appended here. So our new code word will be 1001110, and this total code word is transmitted in the other end. Now our question is how receiver will detect if there is any error occurs or not. So what the receiver will do? Receiver will receive the same code word. The receiver will receive the same code
তাহলে এই
word.
প্রথম লাইনটা কি করে এলো সেই সময় শোনা যায় না, আমি ওই জন্য কমেন্টে বলছিলাম প্রথম লাইনটা কি করে আসছে প্রত্যেকটা ক্ষেত্রে। এই যে মানে আর্গুমেন্টের ডেটা ওয়ার্ডটা 1001 কেন
কোনটা 1001?
প্রথম লাইনটা যেটা আর্গুমেন্টের ডেটা ওয়ার্ড লেখা, এটা এইভাবে আর্গুমেন্টের ওই তার পাশেই লিখেছেন ডিভিডেন্ড।
ডিভিডেন্ড দেখো এই 1001 তো উপরে বলেই দিয়েছে, এটাই হচ্ছে আমার ডেটা যেটা আমি সেন্ড করব, অরিজিনাল মেসেজ।
হ্যাঁ মানে তারপর ট্রিপল জিরোটা কেন হচ্ছে?
ট্রিপল জিরোটা হচ্ছে দেখো ডিভাইজারের লেন্থ কত 4, 4 মাইনাস 1, তিনখানা জিরো তোমাকে অ্যাপেন্ড করতে হবে ইনিশিয়াল, মানে রুলটা হচ্ছে n মাইনাস 1। এবার তোমার ডিভাইজারের লেন্থ যদি হয় 8 বিট, তাহলে তোমাকে 8 মাইনাস 1, 7খানা জিরো অ্যাপেন্ড করতে হবে আফটার ইওর অরিজিনাল মেসেজ।
আচ্ছা ঠিক আছে।
So now we will see what will happen in the receiving end. In the left hand side picture, it shows the receiver receives the exact bit value that was sent by the sender. So the receiver receives 10011110. The receiver doesn't know which part is the CRC, which part is the original message. So as a whole, the receiver will perform the same method as the sender was done in the same way. So the divisor was predefined. So the same divisor will use in the CRC part, in the CRC checker part. But this time, as a whole, 10011110, the total code word is divided by 1001 in the same way. And if there is no error message in the bit stream, then the remainder should be 0, all 0. So if all 0 remainder is found, that means there is no error in the bit stream. So now the receiver will crop. Now the receiver will discard the last 3 digits, that is 110, that was appended from the LSB side. Those last 3 digits will be discarded by the receiver and the exact original message is received. So receiver will receive 1001. That was the original data message. That sender wants to send. তো এটা হচ্ছে এরার না হলে কি হবে। এবার দেখো রাইট হ্যান্ড সাইডে আমরা দেখাচ্ছি যে এরার হলে কি হবে। Suppose instead of 1001,110, the receiver receives the data value 1000,110. So fourth bit from the left hand side has been changed. Now we will see what will happen. Actually, the receiver doesn't know anything. Receiver just receives the bit pattern in terms of signal. So according to this, the bits are represented. So after getting the signal and converted this into bits, the receiver receives the receiver understands that it is the bit value 1000,110. Till now, receiver is unaware about whether any error occurs or not. So what the receiver will do? Receiver will divide the total bit stream with the predefined value 1011 in the same way. But this time, instead of 000, some other bit pattern is generated as a syndrome after the CRC pattern. So that means there is some remainder other than 0. So if the remainder is something else other than 0, that means there is an error in the bit pattern. So immediately that data value is discarded. The entire data value is discarded. বিশাল এবার ক্লিয়ার হয়েছে?
ইয়েস স্যার। স্যার একটা কোশ্চেন আছে, ডিভি স্যারটা কিভাবে ঠিক হচ্ছে, ডিভি স্যার ভ্যালুটা?
ডিভাইসের ভ্যালুটা তোমাদের প্রোটোকলে ডিফাইন থাকছে, ঠিক আছে? তোমার সিআরসি মেথডটা কোন সিআরসি তুমি ইউজ করছো তার উপর বেস করে ওটা প্রিডিফাইন থাকে।
আচ্ছা, ওকে স্যার।
ঠিক আছে, ওটার একটা প্রিডিফাইন ভ্যালু থাকে কিছু। যেমন আমি যদি এক্সাম্পল বলি, এক্সাম্পলটা দিয়েছি কিনা আমার খেয়াল নেই, না এক্সাম্পলটা বোধহয় দিই, এক্সাম্পলটা দিই। ওইখানে কিছু কিছু অলরেডি প্রিডিফাইন্ড আছে, যেমন 8 বিট ডিভাইজার হলে কি হবে, 4 বিট ডিভাইজার হলে কি হবে, 16 বিট ডিভাইজার হলে কি হবে, 32 বিট ডিভাইজার হলে কি হবে, এগুলো সমস্ত প্রিডিফাইন্ড আছে। ওকে
ওকে স্যার, ওকে স্যার।
তো সেই অনুযায়ী ওটা কাজ হয়। Okay, now there is another thing, that how the things are represented, how these bit patterns are represented. If the bit patterns are too long and there are more number of zeros in the bit pattern, then it is not the suitable way to show, it is not the suitable way to represent the bit values in zeros and ones. So we will adapt a different way to represent the values. What is the different way? The different way is to represent the values with the help of polynomials if there are more number of zeros in the bit pattern. Okay, so polynomial can be used to represent the binary word, and we will see how this can be done. Suppose we are taking this bit pattern 1 0 0 0 0 1 1. So how many bits are there? 1 2 3 4 5 6 7. 7 bits are there, and out of that 7 bits, 4 zeros are there. So more number of zeros are there than the number of ones. So it is not suitable to represent this value as 7 bit 10000011. It is not suitable. So what we will do? We will represent it in terms of polynomial. See, in the LSB part, in the LSB location there is a 1. So treat this as x to the power 0. So it should be multiplied by 1 into x to the power 0. So it is 1. Then next bit, A1 bit, there is 1 again. So it is again multiplied with 1 into x to the power 1. Normal যেভাবে আমরা binary calculation করি, x to the power 0, x to the power 1, x to the power 2 and so on. And just multiply the data values along with this x to the power values. And if the data values are 0, then those terms will be eliminated. Ultimately, there will be only 3 terms. Okay, rest of the 3 terms are kept. That is x to the power 6 plus x plus 1. So in this way, we can reduce, we can represent the data values in shorter format. আমাকে 7টা বিট দিয়ে রিপ্রেজেন্ট করতে হলো না, আমি একটা পলিনোমিয়াল ভ্যালু দিয়ে ছোট করে রিপ্রেজেন্ট করব। কিন্তু তার আগে বুঝতে হবে যে এটা কোথায় সুইটেবল, যেখানে নাম্বার অফ জিরো বেশি আছে বিট প্যাটার্নে, যেখানে নাম্বার অফ 1 বেশি আছে সেখানে কিন্তু এই পলিনোমিয়াল রিপ্রেজেন্টেশন এর কোনো মানে নেই। ডেফিনেটলি এটা কাজ করবে, একইভাবে কাজ করবে, কিন্তু তার কোনো মানে নেই। ওকে, so you can see how the same thing happens, how the CFC division method is used using polynomial. Here the data word is x cubed plus 1. Okay, so the dividend has been generated according to that. The divisor is x cubed plus x plus 1. Okay, x cubed plus x plus 1. Okay, now we will normally perform this method and we can find out. But the problem is, if this type of problem are given in the question paper, then it is not a very good strategy to find out to perform this CRC method in polynomial format. So what you can do, you can represent the polynomial to 1-0 format. Then you can do the simple division like thing, simple subtraction like thing, and then the result can be converted into polynomial again and can be written as answer. Now this is another example of CRC, a different example. Here the original bit value is 1010000. 1 2 3 4 5 6 7. 7 bit. The sender wants to send 7 bits, and the divisor value is 1001. So how many bits are there in the divisor? 4. So value of n is equal to 4. So n minus 1, that is 3 redundant bits are appended along with the original bit stream. So here you can see in the left hand side, those redundant bit values are shown in red color. Okay, then we will perform the same thing. If the 4 number of bits are there in the divisor, so we will take first 4 bits from the dividend, check whether the MSB is 1 or not. If it is 1, then it goes 1 time, so we will write the divisor 1001 and we will subtract. Bitwise subtraction is done, and in the same way the same thing happens. Okay, and ultimately 011 is the remainder. So that the initial 3 zeros, those were appended as a redundant bit. These 3 zeros are substituted by the 011. Okay, and the total bit stream is transmitted. So this is the message transmitted 10100000. That is the original message, and the CLC is appended 011. 011 is the CLC that is appended here. Okay, and receiver will receive the same thing, and it will perform the same method, and ultimately there is no remainder. If there is no remainder, that means there is no error in the bit stream, hence the data is accepted.
স্যার আগের স্লাইডে সিলেক্ট এই স্লাইডে এনএসবি যখন জিরো তখন তো সব করে জিরো হওয়ার কথা নেই, যেটা দিয়ে আমি সাবট্রাকশন করবো।
এটা দেখো, এটা একটা জায়গা থেকে আমি ছবিটা নিয়েছি, জিনিসটা ঠিক আছে বলে। এখানে এমএসবি জিরো কোথায় পাচ্ছ তুমি বলো?
মানে সেকেন্ড যে সাবট্রাকশন করে 0011 বাকি সব করে জিরো, এনএসবি জিরো আছে তাহলে বাকি নিচে সব করে জিরো হওয়ার কথা। তাহলে
110, ও হ্যাঁ, এখানে একটা ওরা স্টেপ জাম্প করেছে, এখানে ওরা স্টেপ জাম্প করে পরের স্টেপটাকে এখানে লিখে দিয়েছে। দেখো এখানে প্রত্যেকটা বিট একটা একটা করে শিফটিং হওয়ার কথা ছিল, এইখানে দেখ একসঙ্গে দুটো বিট শিফটিং হয়ে গেছে। এই জিরোটা শিফটিং হবে, এখানে একটা জিরো হওয়ার কথা হয়ে এই জিনিসটা তার পরের স্টেপে আসার কথা, এখানে অ্যাকচুয়ালি স্টেপ জাম্প করে আর কিছুই না।
হ্যাঁ, ইয়েস স্যার,
স্টেপ জাম্প করে শর্টার ফরম্যাটে দেখানো হচ্ছে। এই এক্সাম্পলটা যেটা দেখানো রয়েছে এটা হচ্ছে একদম প্রত্যেকটা স্টেপ দেখানো রয়েছে। এই স্টেপটা ওরা জাম্প করে এইখান থেকে একবার এখানে চলে যাচ্ছে, ওই জন্য দুটো জিরো শিফটিং হয়েছে। দুটো জিরো শিফটিং হয়েছে, দুটো জিরো শিফটিং হয়েছে, এখানেও তাই হয়েছে, দুটো জিরো শিফটিং স্টেপ জাম্প করেছে আর কিছু না। Next, we will decide checksum. This checksum method actually follow the arithmetic technique. So what we will do? First, we will divide the total message into several groups, where in each group an equal number of bits are there. Suppose, if in this example, if we divide the total message into k different groups, and in each group there will be n number of bits. Okay, then we will add the data values of all those groups, and we will found a summation. Suppose we are adding our value of n is equal to 4. So we have divided the whole thing into k groups, and in each group there are 4 number of bits. Now when we add all those things, it may happen some carry is generated. If any carry is generated, that will be added with the summation result as an n around 10, and then we will find out the ultimate sum, and then that value is complemented and the checksum is generated. After the complement, one complement, okay, and the checksum is generated. Then the total data value along with the checksum, তাহলে checksumটারও লেন্থ কত হচ্ছে, n bits হচ্ছে। ওকে, সো বেসিক্যালি আমাদের k খানা গ্রুপ পাঠানোর কথা ছিল, instead of sending k different groups we have to send k plus 1 group, কারণ checksumটা অ্যাড হয়ে গেল। ultimately total message আমরা k গ্রুপে ভাগ করেছিলাম। Then again a checksum is generated, and we are appending that checksum part along with the original data. So ultimately we are sending k plus 1 group. Okay, so while this is received in the receiver end, receiver will again, according to the protocol, receiver will again divide the entire bit stream into k plus 1 group, where in each group n number of bits are there. Then all the things are added, and then the result of the summation is complemented. If after the complement, obviously once complement, if the result after the complement operation is all 0, that means there is no error. But if any data bit value has been changed during the transmission, then obviously it leads to an error. So here is the method for the sending part. The message is divided into several groups into 16-bit words, suppose. The value of the checksum word is initially set to 0. All words including the checksum are added using one's complement addition, and the sum is complemented and becomes the checksum. And the checksum is sent along with the data. Whatever I have said right now, that is written there. And in the receiving side, in the receiving end, the total message including the checksum is divided into 16-bit words, and all the words are added using one's complement addition, and then the sum, the result that is found, that value is complemented and becomes a new checksum. If the new checksum value is 0, that means the message is accepted, otherwise it is rejected. We will see this with the help of an example. Here you can see. This is the original data. The original data has been divided into 4 different groups. 1, 2, 3, and 4. And those 4 different groups has 8 bits each. You can see 8 bits are there in group A, group 1, 8 bits are there in group 2, 8 bits are in group 3, 8 bits are in group 4. So all the group data values are added. First, data value of group 1 and group 2 is added. And you can see, while we are adding 2 8-bit data, the result may be of 9 bits. It happens for every addition operation. Due to n bit value যোগ করলে maximum resulted length হতে পারে n plus 1 bit. So if any carry occurs, we will add this carry in this way. This is called add an end around carry. So এই যে ক্যারিটা যেটা জেনারেট করছে, এই ক্যারিটা সামেশনের সঙ্গে অ্যাড করে দেবো। যেটা যখন অ্যাড করে দেবো, এটা তাহলে 1 1 0 হয়ে যাচ্ছে, সামেশনের রেজাল্টটা চেঞ্জ হয়ে যাচ্ছে। Ultimately the summation result is of 8 bits. Then with that data value, we can add the contents of group 3. Then with that data value, with that result, we can add the content of group 4. And if any error occurs, if any carry occurs, carry will be added as an end around carry, and the sum is generated. This is the sum 0 0 1 0 0 1 0 1. Now we will perform one's complement and we will get checksum. দেখো এখানে জাস্ট ওয়ান্স কমপ্লিমেন্ট করে চেকসামটা করি। এবার রিসিভিং সাইডে কি হচ্ছে? In the receiving side, first তাহলে কটা আমরা পাঠাচ্ছি, টোটাল ডেটা কি পাঠাচ্ছি? ইনস্টেড অফ সেন্ডিং 32 বিটস, এখানে 4টে গ্রুপ আছে, এই 8টা করে বিট আছে একটা গ্রুপে, তাহলে 4 8 32. Instead of sending 32 bits, we actually are sending 40 bits because 32 bits are there in the original message and 8 bits are added, are appended actually as a checksum. So in the receiving side, receiver will divide the total data value by 8. Then the receiver will understand, okay, there will be 5 groups. So equally the data values are divided into 5 groups, where in each group 8 bits are there, and all the bit values are added. All the group values are added. Group 1 is added with group 2 group. The result, the group 2 is added with the resultant of group 1 and group 2. Then group 4 is added. Okay. Then this is the checksum 1 1 0 1 1 0 1 0. Here you can see the checksum 1 1 0 1 1 1 0 1 0. So this is also added, and we will get the sum. Then the sum is complemented, and we will, if we get all zeros as a complemented output, then the result is okay. So the data values are accepted. Okay. এখানে তোমরা একটা কথা বলতেই পারো যে যদি সাম সব 1 1 আসে at the receiving end, that means it is okay. If the sum values are all ones, that means its complement should be 0. So what is the need for additional complementer circuit? It needs because sometimes the receiver wants to send message using checksum. So at that time, receiver needs to follow the same method. That's why receiving end and sending end method তাকে সেম করার জন্য এই অপশনটাকে রাখা হয়েছে। So here is another example. The same thing happens here. Okay. the data values are changed. So this is the checksum method. Now, give your attendance first, then I am talking with you if any doubts are there or not. Vikas Kumar Jadhav,
Present, sir.
present. Tapadipto, present.